Hey, welcome back. This is Keith Wiggins with PAG Waste Management. We're going on Chapter 5 here of Handbook of Biomass Downdraft Gasifier Engine Systems. Sorry for the long delay. We've been working on some cool stuff, and hopefully I can share that stuff with you in the near future here. I think we're on unanswered questions about the stratified downdraft gasifier. Let's see if that's exactly where we left off. Um, yeah, you know what? I think we're on 5.8 stratified downdraft gasifier. And if we're not, it's fine. We're going to talk about this again. So, new type of gasifier, which we have named the stratified downdraft gasifier, also called open top or topless gasifier, has been developed during the last few years through the cooperative efforts among researchers at SERI, the University of California in Davis, the Open University in London, the Buck Rogers Company, and a bunch of others. Is also Buck Rogers Company. That's hilarious. Back in the 80s. Also related to the Chinese rice hull gasifier, the stratified downdraft gasifier overcomes many of the difficulties of the embedded gasifier and may ultimately be the basis of improved gasifier designs. However, it has not been widely commercialized at this point. The reader must balance the proven reliability of the gasifiers discussed above against the promises of the stratified downdraft gasifier. Um, Description of stratified downdraft gasifier. The stratified downdraft gasifier consists of cylindrical vessels with a hearth on the bottom, as shown in figures 510 through 512. During the operation, the stratified downdraft gasifier, air and biomass pass uniformly downward through the four zones. Let's see if we can expand this a little bit more. That's fine. No problem. I'm gonna give us a little bit more of a magnification here. Hence the name stratified. The open top ensures uniform access of air or oxygen to the flaming pyrolysis zone as opposed to the embedded gasifier. The uppermost layer is composed of unreacted biomass fuel through which the air enters. In the second layer, the biomass reacts with the air in the flaming pyrolysis. The third layer, which was made up of char from the second layer, reduces the pyrolysis gases. Inert char, which constitutes the fourth layer, normally is too cool to cause further reactions. However, since the fourth layer is available to absorb heat or oxygen if conditions change, it serves as both a buffer and charcoal storage zone. The temperatures and chemical compositions in each zone are shown schematically in figures 5.10. The top zone of the stratified downdraft gasifier may be adjusted to any depth during air operation and serves the same function as the fuel magazine in the air gasifier. Fuel is added through the open top of the gasifier and should be replenished before the advancing pyrolysis front consumes all the available fuel. During oxygen operation, the advancing pyrolysis front moves much faster and is stabilized at the top of the second zone, so there is no first zone of fuel storage. Biomass must then be fed regularly into the top of the flaming pyrolysis zone, and the second zone must be closed and insulated above, forming a burner section. Air reacts air reacts with pyrolyzing biomass in the second zone, and most of the volatile wood is burned to supply heat for the pyrolysis, as explained in Chapter 4. We have called this process flaming pyrolysis and distinguishing it from flaming combustion, which occurs in the absence of solids with excess air or oxygen. At the bottom of the second zone, the biomass has been converted to charcoal, and all the oxygen from the air is reacted. The final gas leaving the second zone contains carbon monoxide and hydrogen, as well as carbon dioxide and water, produced in the earlier stages of combustion, as shown in Figure 5.10. The carbon monoxide and hydrogen mixture is already sufficiently concentrated to a combustible gas at this point. The hot gases produced in the flame pyrolysis zone react with charcoal in the third, or char gasification zone, to convert more of the carbon dioxide and water into carbon monoxide and hydrogen. Through the Boudard and water gas reactions, we call this process abiatic char gasification. Abiatic means no heat flows into or out of the section. During the reaction, sensible heat of the gas is converted into chemical energy of the fuel gas. This results in cooling the gas to about 800 degrees centigrade, a temperature at which no further reaction is possible. Finally, there may be a zone of unreacted charcoal below the char gasification zone through which the gas must pass before it reaches the gate. The last zone is the disadvantage that char and ash from the char gasification zone must also pass through it to reach the grate. However, as we mentioned before, it provides a buffer or reservoir of charcoal that is available to accommodate changes in power level, which otherwise might cause grate to heat excessively. The stratified downdraft gasifier has a number of advantages over the in-bare gasifier. The open top permits fuel to be fed more easily and allows easy access for instruments or measure conditions within the bed. The uniform passage of air and fuel down the gasifier keeps local temperatures from becoming too high or too low, while the average temperature is high. The cylindrical construction is easy to fabricate and permits continuous flow for otherwise troublesome fuels without causing bridging or channeling. Finally, the various strata are more accessible for measuring compositions and temperatures within the bed so that it is possible to compare modeling results with empirical observations. The stratified downdraft gasifier is both conceptually and mathematically easier to comprehend. Quantitative descriptions and mathematical models of gas flowing through the bed are thus facilitated. In principle, the gasifier can be scaled to large diameter because it operates as a plug flow reactor, and the air and the fuel are uniformly mixed. A 0.6 meter internal diameter gasifier has been operated successfully by Buck Rogers Company of Kansas. 0.77 meter internal diameter gasifier to produce 750 kilowatts of power has been developed by Syngas Systems and is being operated extensively on air and oxygen. We believe that these advantages, coupled with the design simplicity, may ultimately allow the stratified downdraft gasifier to supplant the Ember and other earlier gasifiers, and that a number of design variations will grow from the basic stratified downdraft gasifier described here. Nevertheless, several years of experience with these gasifiers using both oxygen and air have uncovered questions that must be understood and resolved in any commercial design. Unanswered questions about this type of gasifier. The foremost question about the stratified downdraft gasifier design concerns char and ash removal. As the charcoal reacts with the gas in the char gasification zone, it eventually reaches a very low density and breaks up into a dust containing all of the ash as well as a percentage of the original carbon. This dust may be carried away partially by the gas. However, sooner or later, it will begin to plug the gasifier, so it must be removed by shaking or stirring. In-bare gasifiers have a provision for shaking the grate, and when to power vehicles are largely self-purging. Yet, it is desirable to gasify as much of the char as possible before its packing increases the pressure drop. Minimal char ash removal can be accomplished automatically by removing pressure sensing switches, by using pressure sensing switches that activate the removal mechanism only when the pressure begins to build. It is desirable to gasify more than 95% of the biomass, leaving only 5% char ash. The ability to remove variable amounts of char with a moving grate adds a second design issue to the stratified downdraft gasifier. Char consumes more than twice the mass of oxygen required for biomass pyrolysis, and hence high char conversion increases the overall oxygen biomass ratio. If up to 10% of the biomass is removed as char ash at the grate, then the oxygen fuel ratio decreases. In turn, the temperature of flaming combustion decreases, and the resulting gas has both a higher energy content and a higher tar content. This added control of oxygen biomass ratio has not been well defined. A third issue in the design of the stratified downdraft gasifier is the prevention of bridging and channeling. High-grade biomass fuels such as wood blocks or pellets will flow down through the gasifier under the influence of gravity. However, other fuels such as stringy chips, sawdust, and rice hulls can form a bridge, preventing continuous flow and giving rise to very high temperatures. Obviously, it is desirable to use these widely available biomass residues. Bridging can be prevented by stirring, shaking, or agitating the bed, and since the temperatures in the gasifier are relatively low, it is possible to use a stainless steel central stirring arm, such as the one shown in Buck Rogers' gasifier. A fourth issue to be addressed in the design of stratified downdraft gasifiers is bed stabilization. When the gasifier operates at a stable, steady state, the flaming pyrolysis zone advances into the biomass at the same rate that the char is consumed, resulting in stationary reaction zone at a fixed level in the gasifier. However, this zone can move up in very dry fuels, consuming the fuel reservoir and merging at the top of the gasifier. Since no more fuel is available, the gasifier will operate in this top stabilized mode, but there is a substantial heat loss through the open top. This results in lower conversion efficiency and should create a fire hazard and could create a fire hazard. Um, the different gasifiers in the top stabilized mode had closed refractory tops and a pressure feeding apparatus. Fuel must be added at a steady state to prevent alternative pyrolysis and char gasification operations, which can generate high tar levels. We've observed higher tar levels from pulsing pyrolysis process when using oxygen than when using air. Very wet fuels inhibit the flaming pyrolysis zone from advancing fast enough to keep up with the incoming fuel, and the zone subsequently moves towards the grate, consuming the dead char zone at the bottom. The zone may become grate stabilized at this point, or it may continue to move the grate and be extinguished. Thus, control of the reaction zone position is very important in the stratified downdraft gasifier. A number of mechanisms seem to be effective in stabilizing this position, and they are discussed in a recent paper. In summary, both the understanding and commercialization of the stratified downdraft gasifier have made remarkable progress in only a few years of work, but a great deal of effort is still in progress. It is not clear whether this design ultimately will displace conventional InBear and other gasifiers. This is modeling the stratified downdraft gasifier. A mathematical model has been developed at SERI to predict the behavior of the dimensions of the stratified downdraft gasifier. The model is based upon predicting the length of both the flaming pyrolysis and char reaction zones from properties of the biomass fuels and the gasifier throughput. The zone lengths predicted for various sizes of biomass fuels are given in Table 5.4, and the diagram of the gasifier dimension for dry wood chips is shown in Figure 5.13. The predicted pyrolysis and char bed temperatures and chemical composition measured in the char bed are shown in another figure. The interested reader is referred to papers for further details. All right, 5.9, the tar cracking gasifiers. The cost of the gas cleanup system needed for engines used generally exceeds the cost of the gasifier. Furthermore, even if tar impurities are removed in filters and scrubbers, they still must undergo the difficult task of disposal. Therefore, one of the major areas for future gasifier development will be the design of gasifiers that convert the maximum quantity of tar to gas during gasification. Combustion of tars. The tar levels from a number of gasifiers are shown in Table 5.5. 1 cubic meter of producer gas weighs about 1 kilogram at NTP. Therefore, tar levels of 1 gram per meter squared corresponds to a concentration of 1,000 parts per million, or 0.1%. And then let's see here. 1 part per million by so this equivalence in discussing tar levels. It is important to note that updraft gasifiers generate 5% to 20% tar. That's 55,000 to 200,000 parts per million. The downdraft gasifiers in Table 5.5 produce tar in amounts at least an order of magnitude lower than the updraft gasifiers, and new developments are now reducing tars to be in the 100 to 1,000 part per million level. In his thesis, Groenewald used cold flow models to investigate the flow of gases around a nozzle. He found that the incoming air streams entrains and burns tar-laden gas if the gasifier is properly designed. After publication of these results, a gasifier using this principle, central air nozzle, promotes recirculation and combustion of volatiles produced in pyrolysis, was designed and marketed in the Netherlands. The Delicat tar recycling gasifiers was the first tar burning gasifier. It has two solid fuel chambers and a gas combustion chamber on the side. Fuel is pyrolyzed in the upper part of the fuel chamber. Pyrolysis products are aspirated out of the top of the side of the combustion chamber using the flow of combustion air in an ejector where they burn completely at high temperature in the absence of solids. Combustion with air generates producer gas. Combustion with oxygen could generate synthesis gas. The hot combustion products, 1000 to 1100 degrees centigrade, are re-injected at the center of the gasifier. 1/4 of the gas rises through the upper chamber to assure pyrolysis of the biomass fuels. The remaining 3/4 travel down through the lower chamber containing the char produced from the biomass in the upper chamber. The char is gasified by reacting with carbon dioxide and water produced by the combustion as in other gasifiers. The high temperature combustion chamber may permit more thorough deconstruction of the tars. In any case, this gasifier claims to produce very low tar levels. Let's see here. So Santo and Dinakris have developed a gasifier that recycles tars internally in a similar manner, as shown in Figure 5.16. In this case, the combustor is contained centrally in the lower char section of the gasifier, and therefore has very little heat loss. Without recycle, this gasifier produces 1,400 milligrams per nanometer squared, or 1,400 parts per million. With a gas air recycle ratio of 0.85, the tars were reduced in the very low level of 48 parts per million of tar. The high degree of tar destruction in these two units is due to the high tar combustion temperatures promoted by the positive circulation of tars upward away from the reduction zone, and also to the more complete combustion that takes place in the absence of solids. Thermal tar cracking. Temperatures above 800 degrees centigrade rapidly crack the primary pyrolysis oils to olefins and aromatic compounds. These compounds continue to react in the absence of oxygen to make polynuclear aromatic compounds, PNAs, and eventually soot. While high temperatures above 800 degrees can destroy tars rapidly, these same high temperatures also promote reaction with char, which in turn rapidly quenches the gas to 800 degrees centigrade. Therefore, the time available for tar cracking in a bed of hot charcoal is very short. For this reaction, a bed of char may not be very effective in tar cracking as was originally believed. The French croissant loire processes allow a tarry gas from the fluidized bed to be burned further in a separate chamber at 1300 degrees centigrade, resulting in a final gas that is a very low tar content. A laboratory transparent gasifier, a modification of the SCRI stratified downdraft gasifier, has added a tar cracking chamber in which small amounts of oxygen or air can be added to crack the final trace quantities of tar from the gasifier. In the absence of the quenching action of the charcoal, we have measured tar concentrations of 50 to 500 parts per million at the exit from the cracking chamber. However, the difficulty of maintaining a large chamber at temperatures in excess of 900 degrees centigrade causes considerable loss in gas quality at this scale. Perhaps thermal cracking alone is practical in much larger gasifiers. Catalytic tar cracking. Recent work in Europe has focused on producing synthesis gas for making methanol using oxygen and several schemes for eliminating tars and methane. In the Swedish Mino process, the tarry gas from an oxygen fluidized bed is passed through a bed of hydrocarbon cracking catalysts at temperatures between 950 and 1040 degrees centigrade, resulting in a gas containing 10 to 100 parts per million of tar. Dielegis has studied the kinetics of cracking of pyrolysis oils generated at lower temperatures and found that more than 99.9% of these oils can be cracked by dolomite lime at temperatures as low as 500 degrees centigrade. However, these low temperature compounds are cracked and rearranged much more easily than the tars formed at the high temperatures, so the results may not be representative of the difficulty of the gasifier tar cracking. We used the laboratory-sized transparent gasifier to generate typical gasifier tars for testing the kinetics of tar cracking with a number of catalysts in the apparatus. The results of these three catalysts are shown. The variation of cracking rate with temperature is shown in Figure 5.20. For a dolomite lime catalyst, a refinery silica alumina cracking catalyst, and a silicate molecular sieve type catalyst. So those three types of catalysts. Here's the summary. The large number of gasifiers that have been developed over a last century using both experience and intuition. The most successful of these has been the Imbert downdraft gasifier, which produces relatively low levels of tar from uniformly high-grade fuels. We are in a new period during which the principle of combustion science are being applied to develop a better understanding of gasification. New gasifiers, such as the stratified downdraft gasifier and the tar reburning gasifier, promise to expand the range of usable fuels and to produce an even cleaner product gas. Only time will tell whether this increased understanding will result in cleaner, more versatile gasifiers at an acceptable cost. Got some more things here. I might actually do a short video on some of these figures to help explain them. Thanks for listening. We'll get into chapter 6 next time. Talk to you later.